Neural nets do not just make predictions, they build hidden features. A sparse autoencoder lets you force those features to become cleaner and easier to inspect. This is the workflow you'll know how to run when we're done, which trains a sparse autoencoder and explains the top active units. I'm Professor Pi, teaching AI foundations with simple Python. Think of a dataset where inputs mix several simple patterns. You want a compact, interpretable representation. A sparse autoencoder is a small neural net trained to copy inputs to outputs while nudging most hidden units to stay near zero. That creates units that fire only for particular patterns. Practically, this helps when you want features you can inspect, debug, or use downstream in a linear model. At a high level, an autoencoder compresses and reconstructs. Sparsity pushes the compressor to be selective. Success means reconstructions stay reasonable, and hidden units become specialized. In practice, you might run this on a few hundred rows to prototype, then scale up. The tool I use here is PyTorch because it makes small models and training loops easy to read and tweak. The core idea is simple. Train a tiny encoder-decoder to reconstruct a small table. Add an L1 penalty on hidden activations. That penalty is controlled by a weight we call beta. Low beta gives dense features and low reconstruction error. High beta gives sparse features but higher error. We will also measure which unit fires least. Increase beta to push sparsity, and then correlate hidden units back to original input columns to see what each unit explains. We will build a minimal experiment that you can read in a few lines. It uses a tiny 6x4 input grid so you can see numbers at a glance. We train a 2-feature bottleneck, monitor reconstruction error, measure sparsity, identify the least used unit, increase sparsity pressure, and finally compute per unit correlations to input dimensions. This keeps the code small and the concepts clear before you scale up. Now we will construct the tiny autoencoder and measure its initial reconstruction. This snippet constructs a minimal autoencoder in PyTorch and measures how well it reconstructs inputs. The data tensor X is a small 6x4 grid of scaled numbers, so you can see values at a glance. The model uses nn.Sequential with a linear ReLU linear stack to compress to 2 features and expand back to 4. A forward pass produces y, and nn.Functional.MSE loss compares y to the original x for a single reconstruction score. Smaller MSE means better reconstructions, while larger values indicate the decoder struggles to recover inputs. The printed reconstruction error summarizes how faithful the model is at this starting point. Next, we will add a sparsity objective and train. This example adds a sparsity objective and performs training in PyTorch. The optimizer opt is torchOptim.atom, which adapts learning rates for stability. The hidden activations A are taken by calling the first linear, then the ReLU inside model, and Y is decoded by the final linear. The loss mixes reconstruction via nn.Functional.MSE loss with an L1 penalty beta times the mean absolute activation, which encourages most hidden values to be near zero. Increasing beta strengthens sparsity, but can raise reconstruction error. Decreasing it makes features denser, but reconstructions easier. The printed fraction of near zero activations shows sparsity achieved after training, alongside the current total loss. Now we will inspect which hidden unit is the least used across the dataset. This code identifies which hidden feature is used the least across the dataset. It recomputes the hidden activations A by passing X through the encoder part of model and detaches them, so we only analyze values. The vector CNT counts for each unit how many samples have activation above a small threshold, giving a simple usage measure. The function torch.argmin selects the index of the sparsest unit, and then the mean activation of that unit is computed for context. A lower count and small mean indicate a feature that fires selectively. The printed unit index and its average activation highlight the most selective feature learned so far. Next, we will strengthen sparsity pressure and retrain briefly to see the effect. This snippet strengthens the sparsity pressure and measures how many features activate per sample. It raises beta, the L1 weight on hidden activations, and runs a brief atom training loop again to let the encoder and decoder adapt. After training, it computes for each row of A how many units exceed a small threshold and averages across samples to get a single interpretability score. With a higher beta, you should see fewer active units per input, trading off some reconstruction fidelity for clearer, more selective features. The printed average number of active features per sample shows the practical effect of increasing sparsity. Now, we will link hidden units back to input columns using a correlation view. This example connects hidden features to input dimensions using PyTorch correlations. The tensors XC and AC center inputs and activations, so relationships reflect variation, not offsets. Standard deviations, SX and SA, normalize stales, and torch.einsum computes a correlation-like matrix C between each hidden unit and each input feature. The list top J finds for each unit the input with the highest absolute correlation, while gather selects those peak values to summarize alignment strength. If features are sparse and disentangled, each unit should align strongly to a small subset of inputs. The printed indices and average correlation reveal which inputs each unit explains and how confidently. If you map this tiny example to a real system, think of each input column as a sensor or pixel patch. A sparse unit that aligns strongly to one column means it specializes. That specialization makes downstream tasks simpler and models easier to interpret. Recap. A sparse autoencoder compresses and reconstructs while pushing hidden units to be mostly zero. Use it when you want interpretable, selective features that highlight distinct patterns. One caveat: stronger sparsity can increase reconstruction error and may hide subtle combined patterns. Next step: tune the sparsity weight beta to balance interpretability and reconstruction on your real data. Try a small grid of beta values and plot active units per sample versus reconstruction error. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.